In this lecture, we will try to understand a very small but important concept of neutral grounding. This concept will be utilized in the study of power system protection when we will study the relays configuration during various earth faults. Let us see this concept. Usually, there can be 2-3 types of neutral grounding. The first one which we want to study is the system which is having neutral isolated, that is the neutral is not connected to ground by any means. Okay, so let us say we have a generator, synchronous generator. Okay, and this generator is generating balanced voltages. Now this neutral point of this generator is not connected to the ground, that is, it is just like this only. Now let us assume a case that there is a line to ground fault on this one of the phase. Let us say on phase A there is a line to ground fault. Okay, usually line to ground faults are the highest in number which occur in a power system. Okay, so we will see that when this line to ground fault occurs on the system, then there is no completion of the fault path. Okay, so since there is no complete path existing in the system, there will be no current which will flow in the fault. Okay, so we can see that in an isolated system, for the first this single line to ground fault, the fault current will be zero or will be very small. Okay, so what we will have continuous supply to the load even if there is some fault at one point of the system. Okay, so that is why wherever we require a good service continuity, that is, we do not want that power supply to be interrupted on the occurrence of first single line to ground fault, then we may utilize this kind of system. Now this kind of system is having more drawbacks as compared to the benefits. One of the major drawback is the arcing ground and other is the over voltage that we will see just now. Now let us say that the transmission lines are long. Okay, so what will happen? There will be shunt capacitances between phase to ground which will be distributed throughout the line. Okay, there will be capacitances between various phases also, although these will not enter into the picture for single line to ground fault. Okay, so let us say the phase to ground capacitance is C0 and this is C1. Now these capacitances will be distributed throughout the length of the line. Now if the length of the line is very high or there are so many transmission lines connected to the point such that all these capacitances are connected in parallel, then we will see that the value of capacitance C0, the resultant C0, will increase in such a case. Okay, so what will happen? Even if there is no direct path which is visible in the system to the ground, even then, due to the increase in capacitance or the decrease in capacitive reactance, you see that capacitive reactance is inversely proportional to the capacitance. So if we increase this, this will get reduced, and since this is in parallel or in shunt, then it will give a low impedance path to the flow of current. Okay, so even if we cannot see a direct connection between ground, that however, due to increase in the length of the line or the multiple lines are connected to the point, then this will lead to a case that even if a very small line to ground fault is occurring, let us say this line to ground fault is occurring, then it will give a closed path. Okay, however, the flow of current, the magnitude of current will be very low, and it might not be detected by simple circuit breakers or the relay mechanism which is being employed in that system. So this current may continue to exist into the system, or there can be a case that these capacitance and the reactance of the lines may interact with each other, and that may lead to continuous sparking or arcing across the fault. Okay, so this phenomena is usually called as arcing ground. Okay, now we will see how this kind of scenario may result in over voltages. Now let us say this is a case in which we are showing the capacitances to the ground for each phase. Okay, and let us say the system is isolated neutral. Okay, so initially let us say this is EA, this is EB, this is EC, or let me write it as VA, VB, VC, that is this is VC, this is VA, and this is VB, that is the potential of the point for phase A, phase B and phase C. So normally these potential, let us say, are with respect to ground. For a balanced system, this neutral will be at zero potential or the ground potential. Okay, so this point can be thought of as neutral as well as ground. Okay, so the current which might be flowing in the system will be simply the potential across this capacitance. Okay, so the currents flowing into these capacitance will be only these currents, the line to or phase to ground voltage and the capacitance between phase and ground. Okay, so for phase A, the capacitive current will be like this. For phase B, the capacitive current will be like this. And for phase C, the capacitive current will be like this. Okay, so this is capacitive current in phase C, capacitive current in phase A, and capacitive current in phase B. or I have drawn these incorrectly. The capacitive currents will lead the voltage by 90 degree. So for phase A it is correct. However, but for phase B and C, I have drawn them incorrectly. Let me draw it again. For phase B and C, this is the voltage B. Okay, so current will lead the current will lead VB by 90 degree. Okay, similarly for VC, the current will lead VC by 90 degree. So this will be the phasor diagram for normal scenario. These are the balanced voltages. This is neutral or ground, and these are balanced currents. Okay, and their magnitude are equal to omega C naught V phase to neutral for any phase. Okay, now let us say that this phase A is having a line to ground fault. Okay, so you see that in this case what will happen, this ground is no more at the neutral potential. What has happened, this neutral is staying here only because it is the interconnection of these three voltage sources, but the potential of ground is now equal to the potential of this point A. So the neutral has shifted to this point. Sorry, the ground has shifted to this point and neutral is staying here. Okay, so in this faulted scenario, when phase A is connected to ground, directly connected to ground, what has happened? This ground has shifted to A. Okay, so the potential of the healthy phase with, now what are those healthy phases? This is B phase and C phase. These are the healthy phases. Okay. Now what will be the value of potential of phase B and phase C with respect to ground? This will be the potential of phase B with respect to ground, and this will be the potential of phase C with respect to ground. Now you can clearly see that these voltages are equal to the line to line voltages. Okay, and we know that in a three-phase system, line to line voltage is equal to √3 times of line to neutral voltage in magnitude. So you see that in a ungrounded or isolated neutral system, the voltage of healthy phases during one single line to ground fault will rise to the line to line value. That is, normally if it is V, it will rise to 1.732 times of V during just this fault, and this is the steady state value during the fault. During transients, this value may be quite high. So you see that in that scenario, what will happen? We will require extra insulation for various equipment being used in this kind of system. Now we will also see what will be the value of the current, the fault current. Now let us see what will happen to the fault current. Initially, what was the current in each phase? It was equal to J omega C naught V phase to neutral, or VAN. Okay, and magnitude was just like this. Now you see that this A is grounded, so this capacitance is short circuited. Okay, now this is some current, this is some current, and their values are same, omega C naught VCN and J omega C naught VBN. Sorry, instead of N, now it will come G. Okay, now you see that VCG and VBG have now increased to root 3 times of the initial value. So this current has now increased by a factor of root 3. So the capacitive current after the fault is equal to root 3 times of the capacitive current in each phase, and root 3 times of initial value. Okay, so it is in each phase, so it is root 3 times of IC. If IC was equals to omega C naught VAN, then now it is root 3 times of IC. Similarly, it is also root 3 times of IC. Okay, now these currents will try to find a path, return path. Okay, so what will they do? They will go to ground and now return from ground like this to the source. Okay, so this thing, let us say this is current IB and this is current IC. Okay, so this will be equal to the Phasor sum of IB and IC, the fault current. Now let us try to determine the value of the Phasor sum of these two fault currents. Okay, now this is VCG and this is VBG. Now this current IB will be leading by 90 degree the voltage VBG. Okay, so what is voltage VBG? This is voltage VBG, and the current will be leading it by 90 degree. Similarly, this is the voltage VCG and the current will be leading this voltage by 90 degree. Okay, now let us try to find their vector sum or the Phasor sum. So I will pull this down here. Now we will try to find the vector sum. These two are equal. And this angle is 60 degree. We can easily calculate it also. How? Let us see this thing. This is at angle 0. This is at angle 120 degree. And again this is at 120 degree. This is at 120 degree. This is angle 30 degree. This is angle 30 degree. Okay, and this is also angle 30 degree. Now this is VLL and it is perpendicular to this. This thing will be acting like a bisector to this angle. So this will be 30 degree and this will be 30 degree. Now we can also try to find their angle of this current as well as this current, and from that also we can find that this angle is 60 degree. Let us try to find that also. So if this angle is 30 degree, then this angle is 150 degree. Now if this is at angle 150 degree, so what will be the angle of this current? It will be leading this by 90 degree. So the angle of this current will be 150 plus 90 equals to 240 degree. Okay. Similarly, now this is 180 plus 30, 210 degree. So this total angle is 210 degree. Now the current will be leading it by 90 degree. So angle will be 300 degree. So this angle will be at 300 degree. So the angle between these two currents, this current and this current, will be 300 minus 240 or 60 degree. Okay. Now we know that if this is root 3 IC and this is root 3 IC and angle between them is 60 degree, then what will be the resultant? Resultant will be root 3 IC squared plus root 3 IC squared plus 2 times of root 3 IC into root 3 IC into cos of angle between them. Okay. IC squared is common, it will be taken outside. It will be 3 plus 3 plus 2 into 3 into 1 by 2. Okay. So it will be 3 times of IC, that is, it is 9. So 9 under root 9 is equal to 3 only. So you see that the current into the fault is 3 times of what was flowing in normal scenario. So in an isolated neutral system, if there is a fault and the capacitance is such that there is some quantity of current flowing into the system through these capacitances, then if there is a fault, single line to ground fault, then the fault current will be 3 times of its initial value. That we have proved here. Now this capacitive current may sustain continuously because the current value, although it is 3 times of initial value, but it may not be that much high that it can be detected by any relay or MCB or something else, so that it may not be tripped. Because of this, it may sustain, and this may create damage by creation of hot points and arcs. Okay, so these are the drawbacks of this kind of system. Now what we will see, that there is some other arrangement called Peterson coil, which we can use in our system to get similar results of isolated neutral for having good service continuity. Okay, that we will see in the next slide. Now before going to the Peterson coil concept, let us try to understand some 2-3 points. As I have told, that even though this capacitive current is 3 times of its initial value, its magnitude may not be that much high. Okay, so for usually power systems greater than 100 kV, these over voltages during transients especially, may try to influence the design of insulation. Below 100 kV, this insulation is being usually affected by the lightning levels, the thunder, okay? However, beyond 100 kV, this insulation is being determined due to the transient voltages or these kind of over voltages, okay? So, for system especially above 100 kV, what we try to do, we try that this neutral is grounded, or rather we say that it should be effectively grounded. Now, what is the meaning of effectively grounded? What is this effectively means? It means that no matter what is the kind of neutral connection to the ground, whether it is solid connection or through some resistance or through some reactance or impedance, no matter what kind of connection is the neutral with respect to ground, this should satisfy two criteria. What are those? The system's total zero sequence reactance to the total positive sequence reactance should be smaller or equal to 3, and the system's zero sequence overall, this all total zero sequence in this part as well as the neutral, similarly this zero sequence in this part as well as the neutral for x naught as well as r naught, and the ratio with respect to x1, the positive sequence reactance, should be smaller or equal to 1. Now what does it mean? We can see by drawing the graphs of various voltages during various faults, LG fault, LL fault, LLG fault and LLLG fault. We can draw the graphs and we can have various values of x0 by x1 and r0 by x1. We will find from those graphs that if these two conditions are satisfied, then no matter what will be the case or what will be the worst case scenario, even in the worst case scenario, we will find that if these two conditions are satisfied, the voltage of any phase does not go beyond 0.8 times of the line to line voltage. Okay, that is, it is still less than 80% of the line to line voltage. Here it was around equal to the line to line voltage, or it could be more than that, but if we follow this criteria, it will be restricted to this only. Okay, and if you want to see all those curves, then I should refer you to a book called Symmetrical Components by Wagner and Evans. We can ourselves make those graphs by putting various values of these ratios in the formulas which we have derived for various kinds of fault, for various voltages in the power system during that fault. Okay, we can draw or we can clearly see from this reference that if this condition is satisfied, then this is also satisfied, and according to IEEE, this is the definition of effectively grounded. Now you will be surprised to know that even if we directly ground or solidly ground the neutral, there can be a case that these conditions are not satisfied. That is, the system reactance, zero sequence reactance, is greater than 3 times of x1 and system zero sequence resistance is greater than x1. It can be the case. Okay, that is like there is some system which is having some zero sequence reactance here or resistance here, then it can be the case even if that this is solidly grounded, these two conditions are not being fulfilled. Because of this, even though the system is solidly grounded, we cannot call it effectively grounded. Okay, and in that case also, the value of voltage for the healthy phases can be very high, similar to ungrounded system or isolated neutral system. Okay, now for systems which are heavily interconnected, like various mesh are there, various parallel generations are there, so in those case, what will happen if we have effective grounded system? What will happen, or solidly grounded system, that the fault currents will be very high. Okay, so what should we do? How to remedy that? What we will do, we will, instead of solidly grounding the neutral, we will ground it using some reactance. So what will be the benefit of that thing? Now during the fault, current will flow. Okay, either current will flow from this through ground to the fault point. Okay, so this reactance will not have any power consumption due to the flow for fault current. This is the first part. Okay, only reactive hours will be consumed. Second part, we can see that majorly the power system is reactive in nature. Okay, so addition of reactance is going to give more effect as compared to addition of resistance. So you see, if this is R, if I add R into a purely reactive system as compared to addition of X in a purely reactive system, its effect will be lesser as compared to the effect of addition of this reactance. So it will have twofold benefits. First one is that it will not consume any power during the fault. Second one is that it will have better effect. Okay, so that's why for especially system between 69 kV to 100 kV, we usually have reactance grounding. Okay, now there is one benefit of grounding the generators with respect to using some resistance. What is that benefit? That the resistance can consume some power during the fault. Okay, so if we design this resistance that it can withstand the thermal heat or heat generation during the fault, then it will have some stabilizing effect during the fault by first introducing the damping, and second by consuming some power, so that the generator is going to generate at least some power which is being consumed by this, so that the stability limit is little bit higher. Okay, so it will have stabilizing effect because of these two parts. So that's why we can have generators through resistance grounding. Okay, now for systems lesser than 100 kV, where fault currents can be very high due to various interconnections also. Okay, so in that case we use Peterson coil. Okay, now Peterson coil are also known as grounding fault neutralizers, that is ground fault current neutralizers, GFN, or Peterson coil, based on the inventor's name. Okay, now let us try to draw the zero sequence, the positive sequence and the negative sequence diagram of the system during single line to ground fault. Okay, let me erase this first. Let us first draw the zero sequence. You can see that these capacitances will act in shunt. Okay, let us say this is the zero sequence reactance of the system, and let us say I have connected some reactance from neutral to ground. So this will be reflected through 3 times of XL. Okay. Now these will be in parallel with the system zero sequence capacitance. Okay. Similarly, for the negative sequence, what I will have, negative sequence reactance of the system, the negative sequence capacitance. Similarly, for the positive sequence, what I will have, the positive sequence reactance of the line, the voltage, positive sequence voltage, and the positive sequence capacitance. Now all will be connected because it is a single line to ground fault in series. So when I close this switch, it will simulate a fault. Now let us assume that this is catered for in this XL. Okay, that is the effect of X naught is catered for in XL. We are designing the Peterson coil such that we are catering for X naught. Okay, now we want that in this scenario there should not be any fault current. Okay, because in a heavily meshed or interconnected system we want that during the fault there is no fault current, and we can determine the fault just by taking the value of voltage across this reactance. Okay, so instead of detecting the fault through current, we will try to detect the fault through the voltage developed across this reactance. Okay, so what we can do, we can design this 3XL such that it negates the effect of C node. That is, these two are in parallel resonance. Okay, so when these are in parallel resonance, now this will act as an open circuit and there will be no flow of current during the fault. So we can see that 3 times of omega XL should be equal to 1 by omega C naught, or XL, or instead of writing XL I should write only L, the inductance, to avoid any confusion. Okay, in the name nomenclature, L should be equal to 1 by 3 times omega square C naught. Okay, where C naught is the equivalent zero sequence capacitance for the entire network. Now this may change depending upon the fault point. So what we usually have, we have various steps on this reactor so that we can manipulate the value of this reactance to match with the system capacitance, zero sequence capacitance. Okay, but it is a difficult job. Similarly, in this scenario, what we are assuming that the system is balanced. Okay, but there might be scenario that there may not be 100% balance in the system. There may not be transposition of the transmission line. So what will happen, that even during normal loads there will be flow of zero sequence currents. Okay, so the flow of zero sequence current will create a potential drop across XL as well as C naught. Now this thing will act, this load current, zero sequence load current will create a series resonance effect. If somehow there is some resonance, it will create a series resonance effect now. Okay, now we can see that during series resonance, the voltage in the capacitance or the inductive reactance can reach very high value. Okay, so what we need to design, we need to design this reactor's insulation to be at least equal to the line to line voltage of the system. Okay, so these drawbacks are usually seen when the length of line is very large. Okay, when the length of line is very large, these kind of effects, this effect or the single pole to clear ratio or factor, which we will study when we will study circuit breakers, this will impact the Peterson coil design. Okay, so when the lines are very large, we usually do not go for Peterson coil. So since US is a very big country, so usually Peterson coils are not used there, but in Asian countries as well as European countries, Peterson coil are still used for system less than 100 kV. Okay, so in this way I have tried to explain the isolated neutral system, the effective earth system, and the Peterson coil or the ground fault neutralizers. These concepts will be required when we will study various relays and their settings for various kinds of faults, especially earth faults. So this should be easily understood by every student so that we can continue further our study of power system protection. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.